Let's talk about some properties of determinants, and this is going to help us compute determinants faster. So the main problem is with the recursive definition is that it's slow. So it's okay for small matrices or matrices with lots of zeros, but for general ones, it's too slow to be a useful technique. So can we do better? And in this video, I'll show you that we can, and it's the same solution that we've had all semester long, which is we're going to row reduce to win. So the main theorem that we need describes how the determinant of a matrix changes as we apply elementary row operations. So let A be a square matrix. If B is obtained from A using the elementary row operation of replacement, then the determinant of B is equal to the determinant of A. Which means when you're doing row reductions on A, if you ever have to do a replacement, that's where you replace the row with itself plus a multiple of another row, then the value of the determinant doesn't change at that step. If you obtain a matrix B from A using interchange, that's where you swap two rows, then the determinant of B is minus 1 times the determinant of A. So you just pick up a minus sign. And C, if B is obtained from A using the elementary row operation of scaling by some scalar k, then the determinant of B changes by the same scaling factor of k. So basically what we're doing now is we're saying that you can compute determinants efficiently if you're willing to row reduce and do a little bookkeeping. Keep track of which operations you used. So let's take a look at example 2 on page 170 in some more detail. So here we're trying to compute the determinant of this 4x4 matrix A. So the determinant of A, I notice this 2 in the top corner. I would like it better if it's a 1 just to make some of the row reduction steps easier. I can scale the 2 out from that first row and compute now the determinant of the 4x4 that's left. Now I'm going to use row reduction, the elementary row operation of replacement, to use this pivot 1 and kill off all the entries below. Okay? And so I can do that. And now I notice, well, now I have a 1 with all zeros below, and I move on to the next pivot position. The next pivot position is going to be here where I currently have a 3. I can use the 3 to kill off the entries below, and I do that with row reduction. Remember, row reductions are free in terms of computing the determinant, and so the value of the determinant doesn't change when I do these replacements. So now I've used the 1 and the 3. My next pivot position is here where the minus 6 is. I can use it to kill off the minus 3 below. And again, this doesn't change the value of the determinant. And so I get that the determinant of A is equal to 2 times the determinant of this upper triangular 4x4 matrix here. Well, upper triangular matrices are easy to compute the determinant of. It's just the product of the diagonal entries. And so the determinant of A is 2 times the product of the diagonal entries I boxed here in red. And I compute that product, and I get minus 36. So the upshot of all this is the method requires about 2n cubed over 3 operations for an n by n matrix. Now this number is very, very much smaller than the n factorial that's approximately the number of operations using the recursive method. So row reduce to win.